All right, let us use a double integral in polar coordinates to compute an area. So first, let me try and graph the polar function that's being described here. It says it's a cardioid, so I'm just plotting some easy values of theta. Theta is 0, pi over 2, pi, and 3 pi over 2. But then, of course, I can also use a calculator, or I'm using GeoGebra here to graph 4 plus 4 sine theta. They told me it's a cardioid, and I can kind of see why it's named that way after graphing it. They want to know the area that's enclosed by this cardioid that's above the line y equals 3. So I have y equals 3 graphed here, and the way that I'm going to use the double integral to compute this is just express the region using polar coordinates and then integrating the integrand 1. So I need to figure out what these theta bounds are, and then I make a ray in between those two theta bounds and see where it enters and where it exits for the r bounds. So I'm just going to copy this triangle from the picture to get a better sense of what the theta should be. I'm understanding that this point here on the cardioid has polar coordinates given by the function. So the r value should be 4 plus 4 sine theta if the theta value is theta. But then I also understand that it has its own Cartesian coordinates, and I know that the y-coordinate of that point is 3 because the point that I'm focusing on is on the intersection of the line y equals 3 and the cardioid. So I understand that y is 3 on one hand, and on the other hand, y is always r sine theta. So since I know the r coordinate of any point on the cardioid is 4 plus 4 sine theta, I produce this equation 3 equals 4 plus 4 sine theta times sine theta. That happens to be a quadratic in sine theta, so I'm just going to move everything to one side and factor. It does factor nicely into 2 sine theta minus 1 and 2 sine theta plus 3. Only one of those factors is going to yield a solution, however, because sine theta can't be negative 3/2. That's can't get below negative 1. So I understand that the thetas that I see in the picture are the ones that give me sine positive 1/2, which would be pi over 6 and 5 pi over 6. So now I can set up my polar integral. The outer bounds for theta are going to be pi over 6 and 5 pi over 6. And then I go back to that ray that's somewhere in between those two theta values to get my r values. I see it enters the region at y equals 3, so I need to express that as a polar function. Again, y is r sine theta, so y equals 3 is the same as 3 equals r sine theta. Solving for r, I get r as a function of theta. So that horizontal line as a polar function is r equals 3 over sine theta. That's the lower bound of r, and then of course the ray exits at the cardioid, which is 4 plus 4 sine theta. I'm using this double integral to compute area, so I put 1 in the integrand, and the differential unit is r dr d theta. Alrighty, next problem. They ask me to compute this iterated integral not using the usual Cartesian coordinates, but converting to polar coordinates. So first let's just observe what type of Cartesian integral we have. It appears to be a type 2 region. Y is bounded between 0 and 2, and x is bounded between 0 and this function of y. Let me actually inspect this function a little bit more carefully so I can understand it. So x is the square root of 2y minus y squared, which means that x squared plus y squared is 2y. You may recognize that as a circle. And in fact, if you complete the square, so if you subtract 2y from both sides and do the appropriate arithmetic for that, you'll see that this is a circle with center 0, 1 and radius 1. So the first task is to express the region that they're describing in terms of polar coordinates, and typically when you have circular type regions are a little bit easier in polar. Okay, so let me shade in the region that's described here. The y is in between 0 and 2, and the x is in between 0, which is a vertical line at the y-axis, and that function. So we're really talking about this region right here. The first thing that I like to do is determine what theta values bound this region. So it looks like these two theta values, theta is 0 and theta is pi over 2, do the job, and you can verify that once I get the circle itself in terms of a polar function. So let's come back over here. This is the Cartesian equation of that circle, and if I convert it to polar coordinates, well, the left-hand side x squared plus y squared is r squared, and in polar coordinates y is the same thing as r sine theta. So dividing both sides by r, I see that the equation for the circle in polar coordinates is r equals 2 sine theta. And if you plug in theta equals 0 and theta equals pi over 2, you'll get exactly r equals 0 and r equals 2, which confirms that these are the theta bounds that bound the region. Okay, the next thing to do for setting up the polar coordinates of this region is to draw a ray somewhere in between your two theta bounds and see where it enters the region and see where it exits the region. So I can see that the ray enters at r equals 0 and it exits at the circle, which is 2 sine theta. So that means I'm ready to set up my polar integral. The outer bounds are 0 and pi over 2. Those are the theta bounds. And then the r bounds are 0 and 2 sine theta. I need to convert the integrand. X squared plus y squared is r squared. Under a square root makes r. And then the differential unit becomes r dr d theta. Okay, so I'm just going to continue and complete this integral. I can go ahead and integrate r squared with respect to r and make that 1/3 r cubed evaluated from 0 to 2 sine theta. And then when I plug in my theta values, I'm going to end up with a sine cubed. And this is a little bit of a reminder from Calc 2. In order to integrate sine cubed, you're going to want to first write sine cubed as sine squared times sine and convert the sine squared over to 1 minus cosine squared. And that way you can perform a u substitution with u equals cosine, du will be negative sine, and remember to change your bounds of integration here. So when all is said and done, I end up with negative 1 minus u squared du in my integrand, and I'll just complete the integral quickly.